Okay. Next speaker is a final speaker, Dr. Lorenzo Sabattini. He is an associate professor with the Department of Sciences and Methods for Engineering at University of Modena and Reggio Emilia. So if you are ready, please start.
Okay, thank you. Thank you very much. Thank you for inviting me, and thanks for a nice introduction. And sorry for not being there in person, and also sorry for not being able to attend a large part of the workshop because of the time difference. It was a little bit difficult for me. So let me try to share the screen now. Okay. I hope you are able to see my slides.
We can see.
Confirm me that. Okay, thanks so much. So I'm going to talk about legibility, the concept of legibility in multi-robot systems. So how the multi-robot system can communicate to the user essentially. So typically, as we also see in some of the presentations that I was able to attend, the common question is how a user can provide input to a multi-robot system. So for instance, by means of teleoperation or by means of other methods. Here we are trying to use a different perspective. So essentially to answer to the question, how should the group of robots communicate to the user? And why should this happen? Because, for instance, the user needs to share the environment with the multi-robot system, or because the user needs to cooperate with the multi-robot system itself. So by interaction, I mean something that can be very different. So we can have teleoperation of groups of robots. We can have a logistics environment where we have robots used for moving goods, or we can have drones used for exploration, and many other kinds of robots. So it can be we have very many diversified domains, so many different concepts can apply. So the idea here is to understand what happens in the so-called proximal interaction. So by proximal interaction, I mean when the environment is shared, when the user is in the same environment as the robot or as the robots. And so when we need to share the environment, it's important to understand what's going on, because otherwise I, as a user, I will not understand what's happening. I could be scared. I could be not able to perform my job because I'm busy understanding what the machines are doing. And so the legibility is intended as the ability of a robot to communicate its intent to the user. This can happen in many different manners. So the easiest way is to have like some so-called explicit cues. So like you have colored lights, you have words, you use vocal interaction, or you use augmented reality or whatever. The other idea is to use implicit cues. So the way someone is moving communicates their intention essentially, and this can apply to robots. This was studied for like manipulator robots, and we are trying to extend this to multi-robot systems, to groups of mobile robots essentially. So what is specific, what is particular in the concept of legibility extended to groups of robots is that if we have many robots, and if I am a user, I am surrounded by many robots, I have many sources of information, and I can be overwhelmed by this information, in particular if the group is large. So it's not possible, it's not cognitively possible for me to understand each and every specific robot if they are telling me direct information. So our intuition is that with a direct communication by each robot, the cognitive burden would be too high, and so the user would not understand what's going on. So the idea is, if the motion is defined in such a way that it's sufficiently self-explaining, the user would understand what's the objective of the group of robots observing their motion, essentially. So the idea is that to understand how much the motion of the robots can inform the user about the motion itself. So we define a multi-robot system to be legible if this multi-robot system has the ability to communicate the user two fundamental pieces of information. So one information is the so-called spatial goal. So the overall direction of motion of the group of robots, where the robots are moving towards as a group, and also the coordination objective, meaning what the robots are doing in sense of how they are aggregating or spreading in the environment. So as a coordination objective, of course, the coordination objective, as we all know, can be different. We can have many different examples based on the specific task that the robots need to solve. So what we did was to try to abstract this concept and consider a limited number of prototype examples, and we consider the ones that you see now here in the slides. So essentially, the first prototype is the consensus or rendezvous, where the robots are controlled to group in a certain in a common configuration as much as possible. The other is formation control, where the robots are controlled to create a geometric formation, essentially. And the other is coverage, where the robots are controlled to spread in a certain environment, possibly according to a given probability density function. So it can be in a uniform deployment in the environment, or a non-uniform deployment based on a probability density function, as you see here in the picture. And so communicating the coordination objective means, is the user able to understand which one of these three is currently applied by the robots? The other is the spatial goal, which means, so where are the robots as a group moving to? So what we did was to essentially try to define different kinds of overall trajectories for the group of robots and understand if any of them is more understandable for the user. So we consider the global parameter related to the trajectory. So it could be, we considered a minimum jerk trajectory, which, as we also already heard before, is one of the most commonly used also by human operators. So essentially the trajectory is consisting in a straight line towards the goal. And the other one is an arc trapezoidal trajectory, which based on which the robots define an arc before reaching the desired position. And then still related to understanding the spatial goal, we also considered some parameters in the aggregation pattern. So, and we consider these two parameters that you see here, which are dispersion and stiffness. So imagine that you have an artificial potential field creating the connection among the robots. So dispersion is essentially the rest length of this artificial potential field. The stiffness is the stiffness of like a virtual spring defining the potential field. So applying these two parameters, we have a different overall behavior of the system, and we try to understand how much a variation in this parameter could influence the ability of the user to understand the motion of the robot, and which one, if there is a variation, which one of the parameters is the best choice to make the motion more understandable, more legible. We did some experiments in virtual reality. So and the reason to choose virtual reality is that we wanted to have a reproducible situation and to avoid limitation due to the limited size of our lab. So the users, this video is a little bit accelerated. The users were immersed in an environment where a group of robots was moving towards one of these goals represented by the color cubes. And so, first of all, the users were administered a little training session where some examples of prototypical coordination objectives were shown. And then they were, and then the initial condition changed, and the number of robots changed, and also the spatial objective changed. And then the users were asked in repeated examples with different parameters, were asked to answer to the question, what is the current coordination objective, and what is the which one is the spatial goal the robots are moving to. Again, we did experiments in virtual reality in order to be sure to have to ensure repeatability essentially of the experiments. And we did the experiments with non-expert users, so users that were not really aware of that they're not the expert, let's say, in the field of multi-robot system, and of so they were not really aware of what formation control was or what coverage was, so they didn't know exactly what to expect. Then, so the experimental method, we did a within subject experiments where we considered as independent variable the kind of trajectory, the dispersion, the stiffness, and the number of robots. I forgot to put it here. And as dependent variables, we consider the correctness of the response and the response time, both in terms of identifying the correct coordination behavior, coordination objective, and identifying the correct spatial goal. So we did experiments actually in different, in slightly different setups with slightly different modalities. So in the first case, we considered only one group of robots moving in the environment. So all the robots moving in the environment were belonging to the same group. And so the user had only one group to pay attention to. And so the user had to focus on the motion of this one group and understanding the coordination behavior and spatial goal. Then we also did some experiments with multiple groups. As you might see in the video, I'm not really sure. The user is sees in front of her many robots, and the robots have different colors. So essentially, yellow robots are a group, red robots are another group, and green robots are another group. Here we see also top-down motion of the robots. And so in this case, the user was asked to understand for each group which was the spatial goal and which was the coordination objective. And the idea was to try to understand how much confusing it is to have multiple groups with different objectives, and if the presence of multiple groups influences the results that we achieve in terms of preferred parameters, essentially. So let me go ahead. We see some other examples here. Well, the video unfortunately is a little bit smaller than I was expecting, but still the idea is that we see in the top figure, you see what the user sees in virtual reality. On the bottom figure, you see the top-down view of the robots. The user is not seeing this picture here, but we see that in this case, the overall motion of the group is towards this green objective. So the correct answer is the green objective. While here in this case, you see a different motion pattern where the connection among the robots are more loose. So there is more oscillation in the behavior of the robots. And we try to understand if having a more stiff or a more loose coupling among the robots have a difference in the ability to understand. So here I have now a few results. So regarding the coordination objective, so understanding if the robots were performing consensus, if they were performing formation control, if they were performing coverage, we have this the results that you see here in the table. So actually the results are not completely satisfactory in the sense that we have, as you see in the top table, we have a lot of wrong results actually. And which means that actually it's not necessarily easy for a non-expert user to really understand the difference between these three prototype objectives. Then the question could be, was the choice of the prototype objective the correct one? This is something that is currently under investigation. We want to understand that even further. And also, I mean, it's about the actual implementation of the control strategy that instantiate this coordination objective. So you could think of different choice of parameter that could make the understanding easier. Anyway, as we can easily see from the first line of this table, that the consensus is much more easy than other objectives to understand. So this is very recognizable because the robots move toward each other very quickly at the beginning, and so it's very easy to understand. The other thing that we can see is that at least we have this intuition that we tried with different number of robots, with 5 robots only and with 15 robots. Well, with 15 robots, it's easier to guess the correct coordination behavior. So the intuition is that the higher is the number of robots, the easier could be to understand the overall coordination objective, or probably the difference between the behavior in the different coordination objective is more clear if the number of robots increases. Regarding the spatial goal, we had essentially similar results when investigating the presence of only one group moving all together or of multiple groups moving all together. So essentially on the correctness of the trajectory, so on the correctness of the answer, so understanding which one is the correct spatial goal, the trajectory is the most relevant parameter. So having a straight trajectory or an arc trapezoidal trajectory is the fact that makes more different. And actually, the straight trajectory appears to be the most the best choice in the definition of the trajectory. Regarding the time needed to understand to understand the correct answer, so the stiffness appears to be the most relevant parameter. So changing the stiffness so how stiff is the connection among the robots appears to be very relevant in making the motion more or less understandable. The last results I want to show, which are the most recent result that we did, that we achieved, is a comparison with some explicit communication methodologies. So I started at the beginning stating that we want to understand how much implicit communication can be used in the context of multi-robot system, because explicit communication with a large number of robots becomes cumbersome and becomes difficult to process from a cognitive point of view for the user. So we started with this intuition, with this assumption, and then we pursued, we performed all the experiments that I showed you and tried to understand how much implicit communication could be useful. Then we made a step back and said, okay, let's try to see how well implicit communication compares with respect to explicit communication. So explicit communication, we consider essentially 2 classes of explicit communication. One is audio information. So the robots communicate via vocal feedback what is their objective. And then we also use the augmented reality visual information. So the user sees arrows that show, like these ones that you see here, that depict the motion, the current motion direction of the robots. And we try to understand how much implicit communication performs with respect to this one. Our idea was to keep the number of robots limited, so to keep a small number of robots in order to make it still manageable by the user. And our objective was to see how worse the implicit communication could be, in the sense that we are not saying that implicit communication is superior, but at least it doesn't need to have communication means dedicated to only communication. And actually, it turned out that with a user study with 30 users, it was another group of 30 users, the correctness of the answer is comparable with implicit and explicit communication. Actually, implicit communication requires, on average, requires a longer time for the user to understand what's going on, which is something that was predictable, by the way. But still, the fact that the correctness is comparable and that the time is not so much worse is encouraging, in the sense that implicit communication appears to be a viable way of communication, also in the case of multi-robot system, and it has the advantage of not requiring devices or hardware or methodology only to implement communication. I would like to conclude this talk with some acknowledgement, because of course I presented the work, but this was not only my work, and in particular the first name in the list is the name of the person who did most of the work that I presented, Dr. Beatrice Cappelli. She was my former PhD student, and now she is working at System Logistics in Italy. And also the other people that collaborated to this work at different levels are Maria Santos at Princeton, Dr. Valeria Villani, who is my colleague here at the University of Modena Reggio Emilia, and then we have some of our students, in particular Noemi Canovi and Cristina Vercellino, who are currently master students at our university. Here are some of the main publications related to the work that I presented, and well, that's what I have for today. I would be happy to take questions.
Thanks so much. Are there any questions or comments? Yes.
Hi, Lorenzo. Jen here. This
Hi.
is really cool stuff. Hey, how are you going? With the formation that you're using, because you're using motion to provide implicit communication, can you kind of blend the two together? Because you have so many robots in these experiments. Can the formation itself indicate where it's going? You know, at the very extreme, you could make them move in an arrow pointing in the direction.
Oh, yeah. Yeah, this is something that we considered also. And yeah, of course, if you have a formation that is an arrow or that is a triangle or that is a sort of, I don't know, elongated ellipse or a rectangle, this could be inherently some form of communication. And that's the point. But the point in this case, in my opinion, is that you need to heavily modify the task or adjust the task in order to accommodate this idea, in the sense that if you want to explore an environment covering a certain density function and you want to force the robots to create an arrow, then you are like preventing actually a good coverage of the environment, maybe. And so you are diminishing the effectiveness of completion of the task in order to achieve communication. So this could be a trade-off, but it depends on the application. In this case, we try to be agnostic to this and try to consider like general examples in which you are not explicitly going for that. But that's something that, I mean, in a practical application, if you need to study the legibility of a specific application, and in your case it's not a problem to, for instance, create an arrow, then why not doing that?
Mm-hmm. Thanks very much.
Thank you.
Thank you. We have a little time, but let us move to panel discussion. Okay, thanks so much. Let's thank the speaker again.
Thank you. Thank you so much.